Okay. Okay, so today I will talk about a project that we call Artist in Code, which is a direct result of our participation in Bumble. This project is about running Artist in other IDEs than Eclipse, and it uses many technologies that we have developed as part of Bumble, and some others also. So first, I'd like to say a little bit about the goals. Why did we start this? Well, for a long time, we have known that there are other IDEs on the market that are maybe a bit more popular than Eclipse these days, especially for new young developers. So with our two very popular IDEs, Visual Studio Code and Eclipse Thea, they are actually quite similar because they are based on the same code base, which are based on like a web application that you can run either in a browser or in an Electron container as a desktop application. Both of them are also using the language server protocol, which is nice because it means we can decouple the IDE extension from the actual language implementation. And it means that with little effort, we can support more IDEs in the future without having to rewrite the whole language backend, which is the bigger part of this from a code size point of view. And like I said, usage from a web browser is also something that we sometimes get requirement. So people would like to access their models and maybe even do things like building their models without having to install any software. And we also, both these IDEs are, I would call them a bit more code-centric than typical Eclipse IDEs, and maybe also other IDEs. Today in Artists, the approach of working is better described as diagram first. So user creates their models by using graphical diagrams, and then they kind of get the generated code and can start working on code level later. But since these IDEs are very much code-centric, we wanted to see, can we instead give a code first approach where people kind of can start coding and get the diagrams updated automatically as they change the code. And also other, not only diagrams, but also other views. And we also wanted to streamline and simplify our meta model. We have used the standard UML2 meta model for a long time. It's of course working, but it's also very big, and it's unnecessarily big for what we are using and need. So we decided to simplify it significantly, but still remain compatible with the relevant subset, which for us is UML real-time. Yeah, so with code-centric IDEs, it become natural to work primarily on a textual domain-specific language, and we have called this language Art. It's actually not a new language when you look at the concepts, because they are the same that you have in UML real-time, but it's new in the sense that it's a textual syntax that hasn't been defined before. There were attempts in the past in the open source community to create textual syntaxes for UML real-time, but they never took off, and I don't think they ever were implemented seriously in any tool. But this is what we are doing now with this Art language. And this then replaces XML, which is the format used in current Artist for storing models. Having a text-based format that is human readable and the same as you use when editing the model has lots of benefits. For example, it becomes possible to use all sorts of standard tools that operate on text files instead of having to implement special versions of those tools that operate on XML. So it is a quite significant change here, or usability. Then we also wanted to fix a problem that we have today in Artist. Today there is an overlap. So the target language C++ and UML has some overlap. For example, if you want to create an operation in a class, you can do that either at UML level, or you can do it as a member function in C++. And there are many examples of that. And this is a constant source of confusion, especially for new users that come and maybe they know C++, but they don't know UML. And it's kind of confusing. Why is there this overlap? And it has, of course, historic reasons. So we wanted to have a clear separation between the modeling language and the target language, so there is no overlap. Basically, use C++ for what C++ is good at and use modeling for the rest. Another big change is how we view diagrams. Like I said before, in rtist, diagrams are the primary artifact that users start working on and creating, but it also has the drawback that they may look nice when you create them first, but after several years of refactorings, diagrams tend to look messy, and it takes time for people to keep them look nice, and many people don't have that time. So what we see typically when we look at big custom models is that they look like crap. And there are, of course, different ways to address that. One would be to provide commands that can help the user fix these diagrams, and that can be good. But we wanted to explore how far can we come if we base this on automatic layout, so that diagrams are automatically updated as soon as you change something in the model. And we took a similar approach when thinking about code generation, because in rtist, code generation is more viewed as a transformation that you do from your model to something else. But when thinking about it, the generated code is very similar to diagrams. It's acting like a view on the model. So by implementing automatic and incremental code generation that always runs in the background, as soon as the user changes the model, you can get that feeling that the code is always there and it's always up to date with what you have in the model. And then also we are looking at improving the way we generate code, not only to use information in the model, but also do some analysis of the C++ code itself, because we have found that there are some things we can improve if we just could understand a little bit of what the C++ code means. We could, for example, automatically generate certain boilerplate code that has to be used for encoding, decoding, for example, and other things that today users have to write manually, which is quite tedious. So these were the goals, and I want to just to briefly describe a little bit more about these key concepts. So the art language is a new language in the sense that the syntax is new, but the concepts are very old. And this language is then about creating real-time applications that consist of communicating state machines. And we made quite a lot of effort, especially early in the Bumble project. We had a discussion with the MDH, for example, or MDU, about what syntax to use. I think Malvina was involved also here doing some prototyping. And the result is something you can see on the screen to the right here. So we think we arrived at a quite intuitive syntax that has no strange keywords, or should look quite familiar for people that know languages like C++, Java, etc. And remember that C++ developers are our audience. So people that use rtist, they know C++. So anything that looks similar to C++ is better and easier to learn. Like I said, we don't have any overlap, so this language only contains the RT concepts that you cannot easily express in native C++. It's a rather small language. It has about 35 keywords, and I think that should make it also easy to learn. And as you can see in the screenshot, there are embedded C++ code snippets, the gray text there within backticks. That is C++ code that you can place at various locations. And we use C++ for actions, for example, what code to run when that transition is triggered, expressions, for example, what condition to evaluate to decide if a transition should execute, and also declarations. And that is different from rtist, because declarations is anything from additional member variables or member functions in a capsule class, but can also be like an enumeration or even a macro, or basically anything you can write in C++, you can also include. And then we have implemented full support for this language in two IDEs, VS Code and Eclipse. And by full support, I mean all the things that users expect these days from a language, like syntax coloring, semantic validation, which by the way is customizable, as I will show, formatting, navigation, content assist, code actions, and the list is quite long. So diagrams, they are, you cannot only do with the textual notation, because diagrams are extremely important in these kinds of applications. One reason is that it's consumed not only by programmers, but also by other kinds of engineers, like mechanical engineers or electrical engineers that may not be so good at programming, but they certainly can understand the meaning of a graphical diagram, like a state diagram. We support 3 kinds of diagrams that you can see in the screenshot. There are class diagrams, structure diagrams. So by structure diagram, we mean a picture on the parts of a component. I mean, what runtime parts exist and how can they communicate with each other. And then, of course, state diagrams, which is kind of the main way how you describe behavior in these kinds of applications. And like I said, these diagrams are not something you create by a palette and like clicking that you typically do in a drawing tool, but you will get them for free when you're typing in your art files. And this removes the need to manually maintain the diagram, but of course it also comes with consequence that you don't have a full editing freedom to decide exactly where certain elements should be placed. Diagrams are not fully read-only because we do support some editing, as I will show, but they are almost read-only. I think we will. We had a meeting a couple of days ago where many of our customers saw this for the first time, and one feedback we got is that the diagrams are important also for kind of conveying informal information about the system, like comments, colors, and people use the positioning to kind of convey various kinds of meaning that is beyond the model itself. So I think this is an area where we need to continue improve and make for a higher degree of freedom here. Another benefit with these diagrams and difference from rtist is that we support inline expansion. So in rtist, every level of a state machine, and now I'm talking about hierarchical state machines, every level is opened in its separate editor. That has the drawback that one drawback is, of course, that you get lots of editors open. It can become you can be a bit overwhelmed about where to go. And the other drawback is that you get not the best overview, maybe, because you need to look at several diagrams to understand the full picture. So here instead we have the philosophy that symbols that have something inside them get this yellow button that you can see in the state diagram there. And user can click on that button to expand and collapse the symbol at any level he's interested in, or maybe completely expand everything if you want to see a full diagram, or maybe completely collapse everything if he's only interested in the high level overview of what how it's working. And then there was, of course, navigation between both the diagrams and the art files and vice versa. And as a technical side note, we are, as I think also we have mentioned this course many times, we're using GLSP for implementing these diagrams. So GLSP stands for Graphical Language Server Platform. It can be described like the graphical equivalent of LSP. So it's what LSP is for textual languages, GLSP is for graphical languages. And it uses SVG for the rendering, which has the benefit that these diagrams look and behave the same, both when you run them on the desktop and if you access them from a web browser. And then code generation. So code generation, we have decided to make it fully compatible and in fact almost identical with the code that's generated from rtist. The main reason for this is that then users who choose to migrate to this tool in the future don't have to change the code they have written in transitions, for example, because all APIs will be still the same, and the runtime library that we are linking and our applications against, we call it the target RTS, that can be reused. And that's a significant piece of investment that has been around for at least 20 years and used in many products all around the world. Like I said, so code generation in rtist is more like a step that you invoke a command and you run a transformation and you get the type as some kind of byproduct from the model. But here instead we have the philosophy that the code is just another view of the model, just like diagrams is a view. So as soon as you change something in the art file, diagrams are updated. And this has some nice usability benefits also, because it means that if you, for example, choose to write some code for a transition, it's usually best to do that in the context of the generated code and not in the art file. Because in the generated code, you can take advantage of all the editing features provided by the C++ tooling in the IDE, which of course is much better than what we could provide ourselves if you choose to do this inline in an art file. So it's nice to be able to jump back and forth between the art file and the C++ and do the editing where it's most appropriate. And this immediate mapping also helps when the user is learning this, because he can do some changes in the art model and immediately see those changes reflected in the code to kind of understand, especially for someone that only knows C++, he can kind of then build a mental mapping of how do these art concepts actually work? What do they represent in C++? And of course, there is navigation between these two representations also back and forth. So in addition to the generated code, there is also a makefile generated at the same time. And that makefile the user can use for building and also for cleaning, of course, the application. When we are doing this code generation, we of course need some settings that decide. I mean, basically there are lots of things that can influence on how the code gets generated and how the makefile gets generated, and all those are kept in a file that we call transformation configuration. It's a JavaScript file basically, but it has the extension tcjs, and that is actually something we also already have in rtist. We are reusing that almost completely. So now let's switch to looking at this. I will start by just showing you how it looks like in a web browser. So this is Eclipse Thea. I have an art file here for a ping pong sample. And here to the right, you can see the diagram, the structure diagram that shows that this top capsule is like an active class, a class that runs in its own execution context. It has two parts, ping and pong, and it has a connector with these two ports. And these ports here are typed by a protocol, which is kind of like an API for event-based communication. So there are in events and out events. And this shows that the ping and pong can send a ping and a pong event back and forth between each other. While I created this, I will show you later how this was created. But when I did this, I also got this folder generated with lots of C++ and header files and a make file. And if I want to build it, I just go to this place where this was generated and type make. And then this will build the generated code into an executable. And I can then run that executable with a flag here. This rtist debug means that it will not run under debug, or it will run standalone at full speed. Now you see the C++ application sends this event back and forth between each other. So now if I instead switch to, so this was in a web browser. Now if I switch to VS Code, you see that it looks quite similar. That's because VS Code is based on they are sharing the same code base. Thea is kind of, I would say, a derivative of VS Code. It supports the same APIs. But here we have a standalone desktop application running in the Electron container. I have installed the C++ extensions in VS Code, and I have installed rtist code, which is our extension. And then I have opened an empty workspace. And now I can start by creating a new text file. And VS Code supports many languages. And if I click here, you get the list of all languages that are supported. Our language is called Art, which is nice because it makes it appear on the very top here. So let's save this art file in my project here, or folder. Let's call it demo.art. Now I have my art file, and now I can start to create stuff here in my model. And the way to do that in VS Code is to use control space. It's content assist. So this will then send a query to our language server, which now is running here as a Java backend process, and it will populate this list with items that can be created at this particular location in the file or in the model. And let's start by creating a capsule. I will call this demo cap. And a capsule, like I said, it's like an active class that can run in its own thread or in some other kind of, has its own execution context. It needs to have a small state machine. And the very smallest state machine it can have is a start transition, an initial transition, and one state, like it has now. So now I've created this little capsule here, and I can now open the state diagram to look at this capsule graphically, or the state machine of it graphically. So this is an SVG document here that you can zoom in, zoom out freely. It's useful not only for kind of understanding what this means graphically, but also as a way for navigation. So if I double click on these items here, like here, you see the corresponding place is highlighted in my art file. So there is a navigability between these. In the same way, you can, if you select something here and you open the diagram on that, you can see it kind of centers it and shows that will be highlighted. So now if I now create some more things here, and I can create another state like S2, approximately 1 second after I stop typing, this diagram gets updated. And now I see I have a state 2 there. Let's create something else. And if I now put my cursor somewhere here, for example, and do control space, you can see I get now different proposals here for what can be created. And let's create a port. So a port is like, you can say, think about it like a message box where you can put messages or events. So other capsules at runtime can communicate with my demo cap by posting events on this port. And there are many kinds of ports. It's determined by the protocol, which is kind of the type of the port. That is what you see after the colon here. But let's first give it a name. And I think timer is a good name because I want to create a timer port. And that's a built-in kind of port that is provided out of the box by the library. So if I just type the first letter here, because I know it's called timing, and press control space, you can see that this list is filtered to only show the protocols that match this first letter that I typed. So now I have created my port timer. Now let's open another view of this model or another diagram, the structure diagram. And I will put them side by side so you can see both at the same time. I can use this little button here to center the diagram to the viewport, so I get it nicely shown in the middle here. This view shows what capsules exist and how they can, what ports do they have, and how can they communicate with other capsules in the system. You can see now this timer port appears on the frame, which means that it's what we call service port. It's kind of like a public API. So it means that other capsules can post events to this. That's not really what I want, because a timer is something that is only used internally. You to wait some time, and then when that time has passed, you want to get notified by an event. So then let's replace this keyword service here by behavior instead, which is the UML real-time terminology for when something is internal to your capsule. And you can see now the diagram was updated and it shows a different notation here. This comes actually from UML, how this kind of port is shown. So I have a state machine, I have a timer. Now I need to have a transition that can trigger from S1 to S2 when that timer times out. So I go down here in the state machine and I select new trigger transition. Here I am supposed to type, to enter a few information. You see some fields are highlighted here. Those are the ones I need to provide myself. So I need to set my source state or from state to S1, my to state to S2. I need to specify the port, and I only have one. So let's take timer and then use control space here also to see what events do the timing protocol provide. It's only one event, it's the timeout event. So now I have created my transition here that will trigger when this timer times out. And you can see, by the way, that there is a small little blue icon here showing up. This is the same as we use in rtist for showing the user in the, that looks at this diagram that there is some code on this transition, and he can double click on that to get to the code in the art file. So now let's write some code here, and I want to create a simple hello world sample. So let's write some C++ code for printing hello world to a standard output like this. Now I'm using here this cout object, which is part of a standard include header file from C++. So I now need to include that header file for my capsule. The way that can be done is by means of code snippets. So I can go up here in the beginning of the capsule and press control space. And there are some code snippets here that a user from rtist would recognize because they are the same in rtist. We have header preface, for example, which is code that you want to put in the beginning of the header file generated for this capsule. And there's a similar implementation preface, which will be put in the beginning of the CVP file that's generated. And since I'm only using this cout here in the implementation of the capsule, it's enough to do this hash include here in the imp preface. So I will write it like this. And now my hello world sample is almost complete, but there is one thing missing, and I need to set this timer. And a good place where to do that is the initial transition. So I can add some code here by typing this backticks, and then I can go down here and type the code. But there is now also an interesting improvement we made. In rtist, we never do any smartness inside the C++. It's kind of up to the user to write his C++ himself. But here we have taken the advantage to actually allow some smartness. If you do control space here, you see that it provides you with some suggestions. The way this happens is that it analyzes the capsule and understands there is a timer in this capsule. So the user may want to set it. And there are two ways he can set it, either as a one-shot timer, which basically will expire after a certain amount of time and then not expire again, or a periodic timer, which will expire periodically after a certain interval. But for hello world, it's enough for it to expire once. And I get then this little code snippet that actually uses APIs from our target rtist runtime library. And some things are pre-filled here, so I just need to tab here and provide the number of seconds I want it to wait, and then the number of nanoseconds. So let's wait for 2 seconds. And then it's also includes some boilerplate here. Here I should ideally write some error handling in case this timer cannot be set, but let's skip that for now. So now I think this example should be complete. Because if for now I only created the model, I didn't get any C++ code. And the reason is that I don't have any transformation configuration yet. So the tool doesn't know how this should be translated to C++. So let's fix that by now creating a transformation configuration. So you have an option here, new transformation configuration. You need to give it a name. Let's use the default name. And here I can call it hello world output, for example, like that. Or maybe hello world targets, I think is usually what I call it. This specifies which folder do I want this generated code to be placed in. The other thing I need to specify is what we call top capsule. And that's my only capsule, is a top capsule. This acts like the main function in a C or Java program. It's basically the entry point to the application. So when the application starts, this capsule one instance of this capsule will be created and its state machine will start to execute. And this is all I need to create for this small little sample here. So now I can right click on my TC here and activate it because you can have many TCs, because maybe you want to generate code for multiple targets. So at any point in time, only one TC can be active, and that's the one that will be used for code generation. So I activated that. It's indicated by this little check mark to the right. And you saw I got this folder added here, hello world targets. And here I have my code generated. And here under default, there is even a make file. So let's try to build it. I will right click and I will jump to it in the terminal. And I will just type make. That should be enough for this simple sample. Yes, I have built an executable. It's not called top, it's called demo cap. I need to provide this little flag here to not run it in debug mode. So now I'm running it, and you see that after 2 seconds, hello world is printed. That's fine, but maybe we want, as you notice, the application didn't terminate by itself. I had to kill it. And the reason, of course, is that it stays in state S2 forever, since there is nothing more happening in this state machine once it has reached S2. So let's add the code needed for terminating it once it has printed hello world. To do that, I can open the generated code side by side with the art file so you can see how that synchronization also works. We support navigation basically from any element here. So for example, if we take the timer and you right click and do open generated code, the C++ code will be opened and the cursor will be put to the corresponding concept in C++. So here is a member variable that represents this timer. And that's also nice because it makes it possible for users to easily see how a certain art model element has been translated to C++. And it's also useful to do here. For example, if you are in a code snippet, you can just right-click and open generated code, and it jumps here to the CVP file in this case, where this is present. And let's put this side by side so you can see now what happens when I start to modify this this model. So I would like to add another line of code here, and pay attention to what happens down here in the generated C++ code. You see, while I was typing here, shortly after every keystroke, code gets automatically updated. So I always have the same content in my generated code as I have in my art file. So it's very similar to how the diagrams automatically update when I do a change. So now this also means that all I have to do now is to go here and I can build it again. And now it will only rebuild that file that was modified. Because it only updated demo cap. It didn't change this unit name, which is another file generated, and that's why it only did compilation of one file and then it relinked the application. And now if I run it, you will see that if it prints, once it has printed, it automatically terminates thanks to this new line I added here. So what would happen if the user made a mistake? So assume that he wouldn't understand that this context function returns a pointer, but he thinks it's an object, and he would use the dot instead of the arrow here. You can see already down here the C++ features of VS Code will detect this is a problem here because it kind of understands that this will not work. But let's try anyway to build it and see what happens. So now, of course, you get a compilation error, and then you can control click here to jump to that place in here where it's the problem is. And now you can also make changes in this view and get it updated in the model. So the condition here is that you have to change only inside these comment blocks. You cannot make changes everywhere because that we cannot kind of understand how that should be mapped back to art. But here it's easy. So if you change this dot to an arrow again, for example, and do save, you see as soon as I save here, it gets updated in the art file. And that's very convenient because usually when you have compilation problems or other kind of problems, those tools take you to the generated code. And here is also where you get all the nice support. So if I do control space here, I get this cont assist here that I don't get up here, but because here I get kind of the model level cont assist, which also sometimes is useful as we have seen, but it's of course more limited if we're talking about C++ code editing. Yes, so then let's look at another feature. Yeah, we can not only put code here inside the model, but we can also put it outside. So for example, assume I want to have an enumeration in my application. The way to do that in rtist would be to create a UML enumeration in the model, and then that would be translated to C++. But here we can instead do that directly in C++. We can use this declarations code snippet. Here I can once again take advantage of my cont assist to automatically create an enum. I can create some literals, which can be colors, for example. And here I have created it. And notice this little thing here. This is a C++ 11 feature that allows us to annotate any C++ element with our own tags. It's very similar to tagged values, how they work in UML. And this is something we are currently working on to let our code generator look at and detect that if the type has this particular tag on it, then we will automatically generate some boilerplate code around this enum. For example, if the user would like to send this enum across from one capsule to another, then we need to have some function that can serialize it to some format that can be sent across a wire, like text format or maybe a binary format or something else. Those kind of functions are what we refer to as boilerplate code. It's something that is tedious to write. You have to do it for every type that you need to send. So we think we can automate it by just analyzing the C++ code. But it's still work in progress that we have not really finished yet. Yeah, maybe one thing you can also, if you can close this here, see that after a while, the majority of this file actually can be taken up by C++ code, and you can kind of lose track of or lose the overview of what this model is doing. Then you can right-click here and do fold all C++ code. It kind of hides all these or collapses all these sections. You can either then expand them one by one again to see them, or you can use a keyboard shortcut called Ctrl-KJ, which is a VS Code shortcut for expanding all folded sections. There are some other features that I think every user just expects will work, like code formatting. So if I, for example, take this timer and I make it a bit ugly here by introducing some white space, then user can select that, right-click and do a format selection. It will kind of tidy it up, or he can do it on the whole file, just format document. Then we will apply the formatting settings you have made, like, for example, what indentation to use, and reformat the whole art file. There is a nice view here, the outline view, which is quite useful for navigation. So here you get like an overview of what you have in your art file. You can use it for navigating like this. I think also you can, if you start typing here, let me see if I can, sorry. You can jump to the next occurrence here in, this works slightly differently in Thea compared to VS Code. But you can use this for jumping to a particular place in your art file. Of course, you can also do that here by just searching, but then it will be more like a text-based search, and not here. It's more like a model-based outline view search. We use tooltips quite a lot, both as a way to teach the user about this language and also about this model. So, for example, if I put my mouse here over this RT preface, there comes a tooltip telling the user that the C++ declarations you put here, they will be placed in the implementation file that we generate for this capsule. Same as we put it here on this reference, we see that the protocol timing, yeah, it's a timer, and we will get a timeout event. We also have a link here to the C++ library file that implements that timer in case we are interested in understanding how it works behind the scenes. And all these items I have down here, like a state, if I just put a mouse, I get to know that it's a state. I can also do it here from a reference to see it. And I can control click, then I will navigate. If I write some comment up here, like this is my timer, then that comment will also appear if I put my mouse over a reference to this timer. That can be useful as a way to document your application or your model. And same here for this timeout event. This is a predefined event we have written documentation for. Then maybe we should look at, because I showed you how you can change the generated code, but you can actually also do some modifications in the diagram. And currently we support renaming. So if you double click on a state here, you get this little pop-up box. You can then rename the state. And as you see, it will update both the diagram and also here in the art file. And it's actually a refactoring. So it also updates all references to that state in this file and also in other files, if that would be possible to make it consistent. Of course, you can also do the same here. So if you just do rename symbol, you can rename it back, and then it will update here, and after 1 second update also the diagram. So let's create something slightly bigger here in the diagram. Let's create another state, and I will use this to create what we call composite state. So this is a state that has another state machine inside it. We call it S3. And then inside the curly bracket, I can create, let's create another composite state called inner. And inside that, I can create the innermost state like this. And now we can see that we don't show these nested states automatically because it cannot clutter the diagram, but there is this little plus icon appearing here. Here the user can click and gradually choose what level do I want to see. and then collapse again if he's not interested. There is also this possibility to either expand everything or collapse everything to get either the full overview or a very high level overview of the diagram. And this is the same how it works for, so for example, structure diagrams. If we have a nested composite structure of this capsule. Then let's look at another concept called inheritance. So a capsule can inherit from another capsule, so you can reuse parts of other state machines. So if I create another capsule here called base, and I can call its state base state, I can now inherit from this base capsule just as I would do in C++ by typing colon base here. That will then, you see now the diagram was updated with some gray symbols. This is the state machine that we inherit from our base capsule. You also see that there is an error now here. And why is that? Yes, it's because I now have two initial transitions, one, the local one, and one inherited. By the way, I get that information if I put my mouse over here. You see that the state machine of capsule demo cap has two initial transitions, one local and one inherited. I can see the same problem here in the problems view, and here I also can use this double clicking to find these transitions that are conflicting. So how can I solve this problem? Well, one solution would be to delete it from the base capsule, but that's not so typical. More typical is that you redefine it, just like you would do in Java or C++. And to redefine something, it needs to have a name. So that is kind of, I would say, the slight drawback of textual languages, that everything that you want to reference needs to have a name. But let's call it something like init. And now I can go down here and say that this initial transition should redefine the inherited init transition like this. Now you see the error went away. And if it didn't yet update. There are some known issues with this diagram updates that I think we have fixed in a recent build, but still not fully working here. Yeah, now it's updated. I had to restart it, but of course this should happen automatically. So now you see that this inherited initial state now has a green text. That's how we show that this is inherited, and it now targets the local S1 state. So there is no longer any duplicated initial transition. But let's introduce this problem again. Maybe let's introduce another, because not all problems have the same severity. There are also some kind of semantic validations that we do that are more like conventions. So for example, if I create a capsule called my capsule with lowercase, you get a warning indicated by this yellow line. And this is basically every semantic validation has a default severity, but it can be customized. Some of them also has quick fixes, especially those simple ones that we just can fix by capitalizing the name. So then a user can go here and do capitalized name. But if he wants to keep it like this, to really call the capsule like this, he can configure the validation engine so that it doesn't run this particular check on this particular capsule or on any capsule. So I can show you first how to do this locally, because that's typically what you would like to do for this check. You can then go here, do new properties, and if you do control space, rule config, and it should be supposed to be a string. And as you may have noticed, every error has an ID. This one has 0003. So if I type that number here and proceed it with an X, it means that rule will be disabled. You can replace the X with an I to convert it into an information, or maybe elevate it to an error by using E. And of course, you can have a comma separator list here to configure multiple rules. The same thing works globally. So if you go to preferences here, settings, and you type rtist here, you find a similar preference that you can use here. Then it will apply to all your art files in this workspace. And also these hyperlinks are useful because if you click them, you will be taken to our documentation that kind of describes the condition for when this validation can fail, with some useful information that you can use for fixing it. I think this was all I want to show. So I am at the end of my demo. So do you have any questions or comments or thoughts?
Thanks, Matthias. It's very nice, nice work. Let's give some time to the others to ask some questions.
I can ask a question.
Yeah, please, Wim.
Indeed, very impressive. Looks very good. Complete.
Not as complete as you may think.
Yeah, no, but it looks like that.
It's a narrow path.
And also, I like the fact that the code generation and the diagrams, and they all follow the same logic in terms of synchronization and the kind of stuff. I think that's a good thing. And immediate feedback is very important. My question is, did your company build this specific for this language, or is there also, as an outcome of this exercise, some generic tools or whatever, so that different syntaxes or different modeling languages can take advantage of this kind of synchronization and functionality as code generation, etc.?
Yeah, so we have built this using Xtext, as you may know, and it's binding to the language server protocol. So that, I think, is the common library that will be completely reusable if you would want to implement this for another language. I mean, for rtist, this is the only domain-specific language we support. However, we have also showed you here some other languages based on JavaScript, and we are currently actually working on doing the same thing for this little language. Because also here users would like to have things like code completion and highlighting. In this case, we can use the fact that JavaScript is a subset of TypeScript, so we can kind of reuse the TypeScript language server which already exists and only add our own stuff to it. So I think what you will do depends a lot of the language. If it's a completely standalone language like this, then you need to implement it yourself fully, but in some cases you may be able to reuse some existing language server if your language is similar to something else that already exists.
Okay.
But there are also, of course, more work we could do here, like this validation framework is something we implemented, but that of course could work with any meta model, basically.
Yeah.
But it's under the hood. It's based on EMF validation. So it's once again, it's a framework we use that we didn't write ourselves.
But the mechanism that you use for the bidirectional diagram synchronization, how do you do that? What's the technology?
Yes. So the technology here is GLSP, and that is using SVG for its rendering, and it provides APIs that you can use for updating this diagram, for example, when something in the model has changed.
Yeah. Okay. So you're taking advantage of those generic.
Yes, I think probably that is at the level you would use. You would use GLSP, you would use Xtext, you would use EMF validation, but then I think you have to plug your own language into those frameworks. Because,
okay. But you're not aware of significant generic solutions that could help to speed up the development of this kind of functionality, which is still not specific for a certain DSL. If you understand.
No, but it will be really interesting to have it, because I think that would be at least for prototyping, it would be really great to quickly get something up and running. So I think that's an area.
I'm looking for this gray area in between, because I think you had to do a lot of work, even if you have those base technologies that you have used to actually realize this dynamic behavior that works everywhere
Yes, and a large part of that time has been learning these frameworks, because we must be honest, that this GLSP was not trivial to learn. It was in a very early state when we started without any documentation. So we have some team members who fought really hard to understand how it works.
It could be nice if all this learning work would end up in some improvements on those generic frameworks. So
yeah, and I think it has. I mean, now recently version 1.0 was released, and it has significantly improved documentation, for example. So I think things have improved here. Xtext is very stable. That has been around for many years, and EMF as well. So I think this part is the easy part. That the diagram part was the tricky part. To simplify.
Because I think these kind of experience that you now tell us are very important for the community as a whole. Also,
yes.
Yes.
Okay, thank you. Great.
Yeah, thanks.
Okay, it's 2 o'clock, but I have a very quick question. I like very much the nesting component of the models. Does this mean that when I'm modeling a system, I always have one model and then I can simply play with the nesting, or can I have multiple models on the same system?
By models, you mean art files in this case, I guess?
Yes.
Yes, I mean, you can split your model on as many art files as you like. And I think typically here I created my base capture in the same file, but more typical would be to put in a separate file.
In Java or C++.
Yeah, exactly. I think one capture per file will probably be typical, but it's same as in C++. There is no limitations. You can put as many things as you like in one file, or you can use multiple files if you like.
Okay. Other questions, very quick ones. Okay, then I'm stopping the recording.